usual debugger stuff that you would expect to be able to do. There's also a lot of data that is stored within an RSol instance when you create it and attached to a process. And it's structured basically around the way ProcFS structures it. And the example there, you've got the process status information, so the overall process state. You've then got within that lightweight process state, so these are like kind of threads within the process, registers associated with those threads, and then at the end I've got a specific register, the program counter. So there's lots of data hidden in there as well that you can extract and make use of. And that's just a really quick example to show how you would make use of it. Now, here's where I would be doing my special magical live demos, which I'm not able to do because my Spark machine is broken. So it's going to be screenshots, unfortunately, which is not amazing. But it's a console, so it's largely the same thing. So most of these are going to be in IRB, just to show you the kind of stuff that you can do originally in an interactive fashion. Obviously, it's not now. So there I'm just including the library and creating an instance. And then you can attach to a process by PID or name. If there's more than one process with the same name, it's going to give you this little prompt. And once you've selected it, you can see the PID field telling you which process you are actually attached to. And this is an example of the process information that you can get from it. If you simply print the instance, you get a toString method that descends into all of these variables and fields and prints them out. It's a bit hard to read in such large font, but you get the idea. It's going to scroll quite a long way. That's the lightweight process information. You get a lot more specific information there. Registers, a stack trace, including all the register windows. And this is just a very quick example, again, of using basic calls to set breakpoints, stop the process. It can disassemble stuff. You can usually pass it symbols as well as memory addresses in each instance. And yeah, you can also disassemble whole functions at once, and I've passed it there a prefix of address starting with a $, so you can do nice formatting and be able to read stuff quite easily. Okay, so a bit more of a practical example. This is going to basically be how you would implement a process monitor within Sully or within whatever else you're using. I'm just spawning the process here. It's going to spawn the process and just be stopped on the entry point, so you can pass it any values you need or manipulate it however you want before you actually run it. And here I'm creating a fault set. So you can monitor for different faults, different types of faults, and you can monitor for several of those at once. I'm just using one here, but you create this fault set object, which you can then pass in as like a bundle of faults that you want it to trace. So here I'm using the bounds fault, and all these things are stored in constants, so you've got the ProcFS constant class there with obviously the fault bounds. And then you pass in the object and you say, right, I'm going to trace these faults in this process. And if you were now to print which I wish I could do, but I can't. If you were now to print the lightweight process information, you will actually see that it will say traced faults and it will say FLT bounds. And obviously in a normal situation, you'd be passing it in pretty much all of the faults if you're fuzzing, so that you can get a view of all of them. Okay, and then we continue the program, so we're now running the program. And it wants us to give a bit of data, but not too much. Give it a bit more. So there's quite a bit of data in there. And then what I'm calling here is wait for event. One thing that I want to do in the future with this is rework it a little bit so it's a bit of a cleaner interface to be event-driven. But for the moment, you call wait for event, and you can pass it a timeout and things like this as well. This is returned true, which means that an event of interest has occurred and the process is stopped and waiting for you to take some action or print some information. So then I'll print the instance out, and we can see PR stopped, so the process is stopped, and the iStop flag showing that it's stopped on an event of interest. Obviously lots of other information you might want to get from this as well. then you can see why stopped. So here we're getting information about actually why it stopped. It's faulted. It could be also that you've requested it to stop, or it's stopped on a signal if you're tracing signals or system calls. In this case, it stopped on a fault, and it's telling you that it stopped on a bounds fault. You then get a little bit more information about it. Basically, this fault will also generate a signal in the normal run, which will be delivered to the process if you were to continue it at this point. It's obviously a seg fault. The map error gives you a bit of information about why it's a seg fault. In this case, it's an address that doesn't make sense, isn't mapped to anything. You can also get, if you're writing to a region that isn't writable or something like that, you'll get a different flag there. And then the registers, and you can see a lot of 0x61, which is your A's in hex, obviously overflowing things we shouldn't be there. And the return address, very nicely, all A's. So that would be quite a fair indication that you've got some exploitable condition there. Interestingly, in Spark, stacks are not always exploitable in the normal way. You have to have some level of recursion for that to work, but that's beside the point. And this is just an example. I've implemented it within Sully as well, so I've written some wrapper scripts that make it. Obviously, Sully's written in Python, and I've written it in Ruby, but with some wrapper scripts, you can get that to work. I was actually going to show that. I obviously can't. But this is, once you've caught a crash, you can then explore the crash bins in the normal way afterwards. This is a Solaris specific crash bin. And it's just giving you a summary of the crash that it's found there, and some key registers and values that are useful in deciding whether or not this is an interesting crash to you, with the return address and stack pointer and so on being overwritten in a way that might be quite interesting. That crash obviously seems quite interesting to us. So this is another demo here. This is a demo program that I wrote that it's just basically going to give a different message to root to everybody else. So just to show you the normal run of that program, your UID is 100, go away. And this is a system call proxy, which I've implemented with RSol. So a common sort of thing that you can do with other tools, but just as an example. And this is one of the things that in a previous delivery of this talk, I've actually shown writing the majority of this tool, and it's sort of 100 lines, and most of that is making it look pretty when it outputs things. I can't obviously do that now, but I can show you it in operation. So what this does is it traces all of the system calls and intercepts them and lets you take some different actions on them. So this is the GetUID call, and you can block it completely, or you can ignore it and let it go through. So we're going to let it go through, and then this is the system call returning, and it's returning our UID, and it gives you the opportunity to modify that return value, which we will. And we're going to change that to 0, so we're going to look like we're root. And then there's going to be some other system calls that we're not really interested in. We'll skip over. And there, now our UID is root, and the program thinks that we're root. Obviously, that's not going to be a security mechanism I hope anybody would use in real life, but it's just a nice little example of how you can intercept system calls. A more practical use of this would be for things like fault injection. So you would intercept system calls, maybe open calls, malloc, and so on, that you want to, well, not malloc, but that you want to force to return strange values, or you want to force them to return an error state, so that you're running branches of code that you wouldn't necessarily run just from running fuzz cases. It's sort of almost luck if you're going to get a system call that returns an error or not, depending on what resource usage is on the system and so on. So you can do that to basically fuzz more of the code, and that would be a good way of doing it. Also, things like run tracing and code coverage can be done with this. I've implemented a very simple example of that. This uses, I should actually explain before I show this, this uses the Spark instruction type class that you saw in the infrastructure diagram, which is able to search through memory and categorize different instructions that it finds in memory in more specific or less specific ways. And what, in the case of this, it's looking for is flow-altering instructions. So any instruction that can alter the program flow, any decision points